Okay, let us start. So, good afternoon, everyone. We'll start with this new chapter on axisymmetric problems. Now, to be sure, the chapter that we had done before this, combined loading, that also started with a kind of axisymmetric problem, which was the thin walled pressure vessel. And earlier, we did not used to call this chapter as axisymmetric problems, rather, we used to call it thick walled pressure vessels. And as you will see, that will be the first topic that we'll take up. But we have changed its name from thick walled pressure vessels to axisymmetric problems because we are not going to be limited to the thick walled pressure vessels only. We'll take up thin discs and things like that. But the idea is that we'll cover this thick walled pressure vessels properly, and then the lessons that you learn from that will be immediately be applicable to other kinds of axisymmetric problems. So we'll take up this thing. You can call it a problem solution or you can call it a theory, whatever. But the thing is, the way that you are going to approach this chapter, it's going to be significantly different from the previous chapters. Okay, significantly different. And this entire chapter is not there in Beer and Johnson. Okay. It is, however, there officially as part of the Indian Engineering Services examination. So, should you choose to do that sometime, the salary will not be extremely high, but I mean, it comes with a lot of respect. Okay. So, anyway, so we will take up this thick walled pressure vessels. Now, can you give me an example of a thick walled pressure vessel? It will probably not be from everyday life. What? I am not very sure about that. But it may not be an example from everyday life, but it will be examples which you all know about. So, what can be a thick walled pressure vessel? What kind of a thing? Yes, spaceship. Absolutely, spaceship. Okay. Actually, you wouldn't believe it if I told you this. This is so very appropriate an example. This spaceship. Spaceship means basically the rocket structure. Okay. So I had this master student sometime around the pandemic. So after he graduated, not undergraduate, master student, so they also learned certain advanced theories associated with these axisymmetric problems. So he had applied to ISRO, and they have a number of rounds associated, I mean, with the in the interview process. And one of the most important things that they asked him was this thick walled pressure vessel thing. Okay, because it is so very important to them. Okay, so that's it. Okay, another example. Submarine, absolutely, submarine. Okay, anything else? We have already talked about examples of thin walled pressure vessels earlier. Thick walled pressure vessels. Maybe some kind of boilers which have really very thick walls. Okay. Okay, so you take that as homework. Beyond submarines and rockets, what other examples of thick walled pressure vessels we can find out? Okay. All right. Now, the approach. Okay. The approach that we are going to take, as I have already mentioned, it is going to be significantly different. By the way, I just remembered something. Okay, back to the approach. So the approach that we are going to take, it is going to be significantly different from the previous approaches. So here what we will do will look very similar to what you guys did in fluid mechanics. So those of you who love fluid mechanics will also love this chapter. And I'm not making this up, okay? So somehow it has been my experience, because every year I'm checking answer scripts. Somehow it turns out that the girls do very well in this chapter. Somehow they are very much, they have an affinity towards partial differential equations or something. boundary conditions and all these things. Uh, all right. So what are you going to do? So see, in fluid mechanics, you had this Navier-Stokes equation, right? Okay, so irrespective of whether you did fluid mechanics or thermofluid science, you did that. Okay, Navier-Stokes equation, and you did that exact solutions of Navier-Stokes equation for the various special cases. For example, what are the names? The Hagen-Poiseuille flow. Okay, the parallel plate channel. All these things. Okay, so those special situations allowed you to simplify the Navier-Stokes equations to a form which would allow you to find out some solutions, some exact solutions. Because you have probably heard about this, that the Navier-Stokes equation in general doesn't have a solution. It's an open problem in mathematics. Okay, so those issues are there, but for specific problems we have exact solutions. Those questions are asked in mid-semester, end semester also, no problem. So in that same vein, we are going to take it up. Okay, take this thing. So what we'll do is, we will, so there will be some differences. I'll point that out. Now, I'm not going to quiz you. You just tell me whether this, I'm going to write down one equation out of nothing. You tell me whether this looks familiar to you or not. Okay. Does this look familiar? You name it later. Does it look familiar? Yes or no? Huh? No, at least if some term is familiar, okay, पहले देखा है. Okay. All right. Okay, what is it called? Okay, any other opinion? Sorry? Second law of motion. It is actually the second law of motion. Okay, it is the second law of motion. It is not the continuity. Continuity has to do with mass conservation, right? So continuity would be what? So this would be continuity. I'm not writing it here. This is continuity. Okay. All right. Now this equation, you tell me whether this is applicable to fluid mechanics or solid mechanics. Because I wrote it in mechanics of solids class. Huh? Is it applicable to fluid mechanics or solid mechanics? Solid mechanics. Huh? Anything continuum. Very good. Anything continuum. Because Newton's second law doesn't distinguish between fluid mechanics or solid mechanics. Okay. It is applicable for all continuum matter. Okay. So this equation as written, it is applicable to all fluid, solid, viscoelastic, everything. Okay. Of course, for viscoelastic, we have to take care of certain, but anyway, in general, it is applicable. Now, this equation has the name, so it is called the Cauchy's equation of motion. The same Cauchy that we encountered earlier. Okay, so Cauchy's equation of motion. Why Cauchy and not Newton? Because Newton did not express it in this particular form. Okay, so he was not dealing with the stress tensor and things like this. Those came much later, thanks to Cauchy and other guys. Now, what you did in fluid mechanics after this step, okay, so this was also derived in fluid mechanics, even if not explicitly, implicitly it was there. Now, what happened in fluid mechanics was that this sigma, this stress tensor, it was connected to the strain rates. Okay, it was connected to the strain rates. Fine. And the special version of this relation that you learned, the connection between the stress and the strain rate, that was specific to the case of Newtonian fluids that you learned. Okay. Specific to the case of Newtonian fluid. It's a very special kind of fluid, but we teach you time and again because the most common fluid in the world, water, happens to follow the Newtonian behavior. So, and then once you substitute back everything, the equation that you get, that you call as Navier-Stokes equation. Okay. Now, we can do a similar thing in solid mechanics also. Okay, so we have already seen that the material behavior is encapsulated not through the relation between the stress and the strain rate, rather through the relation between the stresses and the strains. What is the relation between stress and strain in solid mechanics that you have learned? The most common one, generalized Hooke's law. That you have studied from your first year. That epsilon x is equal to 1 by E sigma x minus nu sigma y plus sigma z, all those things. So if we take those equations and express the stresses in terms of the strains and we substitute over here, we are going to get an equation. Right, we are going to get an equation where all these things will be present, the dv dt, rho b. What is the rho b? Body force. Body force per unit volume. Okay, per unit volume. So so when you do that, so just like Newtonian fluid, when you substitute the generalized Hooke's law over here, you are going to get an equation. That equation will be called the Navier-Lamé equations. Just like you have Navier-Stokes equation. Okay, so once you substitute sigma is equal to in terms of the strains, you will get the Navier-Lamé equations. Okay, we are not going to study all that. Okay, I'm just telling you for general knowledge. Okay, you should not be completing a course on solid mechanics and not have heard of Navier-Lamé equations. That should not happen. But see, as written, this is the most general version. It has the time dependence, it has the dependence on the body force per unit volume, etc., etc. This body force can be in the form of the forces due to gravity. It could be a body force due to electromagnetic sources also. Okay, so these are the two most common types of body forces. But we are not going to deal with any of those things. From the very first, in our course of mechanics of solids, we have been dealing with situations which are first and foremost confined to static cases. Okay, we have not taken any dynamics course. Okay, we have not taken any dynamic thing, anything involved. So the time dependence is missing, and we'll respect that also in this chapter. So all the time dependence will drop. Do not think, however, that the only important problems in solid mechanics are the ones involving statics. It is not. You can have very much time dependent solid mechanics problems also. Okay, those are very, very rich in physics, but I mean not at second year level. Okay, will not do that. So for statics, this one will not be zero. I mean this one will be zero. Okay, static case. Furthermore, we will consider situations where the body force is not going to be important. Okay, or at least its effects will be negligible. Okay, so this is a choice that we are having. This is not an assumption. Okay, this is not an assumption. This is a choice that we are dealing with those kinds of situations where the body force are not important. Okay, body forces are not important. So what does that leave us with? It leaves us with this thing. Okay, divergence of the stress tensor is equal to 0. Now, if you think about it completely in a mathematical fashion, job is done. Chapter is over. Okay, so this is the end of the chapter. Okay, and like an entire field of solid mechanics is just captured within this. Okay, so tata bye bye, not like that. Okay, so we have to unpack this. Now see, the way that this is written in this compact form, it is very, very useful because it does not depend on whether you are choosing to work with the Cartesian coordinate system or the r theta z coordinate system or the r theta system or the spherical coordinate system. Okay, or any other coordinate system, very fashionable coordinate system. Okay, this one is valid. But when we have to address specific problems, it will be more useful for us to come to more specific versions of this. So what we'll do now, which is appropriate for the second year level, we will first try to understand this equation itself, not through this route. I have told you this only because I wanted you to appreciate some connection with the fluid mechanics things which you have already done in the previous semester. But what I will show you now is a very simple almost like a class 11, 12 kind of derivation for this equation. Okay, in the XYZ coordinate system. We are not going to address the thick wall pressure vessel in the XYZ coordinate system. But what we derive will be a motivation for what we'll do in the thick wall pressure vessel. So step by step, the plan is like this. One thing in this class we have already obtained, that some idea with the fluid mechanics. Next is we are going to see how this divergence of sigma thing can be obtained in a very explicit fashion in the case of solid mechanics, in the case that we choose to work with the Cartesian coordinate system, that is the XYZ coordinate system. Okay, after that I will tell you the rest of the story. Okay, so what we'll do is okay, so I'm going to draw one stress cube. So all this while we have been drawing the stress square, the stress element. This also is a stress element, but we are going to draw it in a cubic fashion. Why? Because we want to deal with the three-dimensional version of it. Okay, so this is the cube. Actually, it's a cuboid because the sides need not be all equal. Now, on this thing, I am going to draw the various components of stresses. Now, everyone, just listen to me very carefully. Put down your pens and listen to me very carefully for 15 seconds. I have said that this is a stress cube, okay, and I have made you remember by saying that it is like the stress element only. But there is one important piece of difference. Earlier, when we were saying the stress element, we drew a square like this. Okay, we drew a square like this, and we said that it is basically representing the state of stress which is there at this point. So what we are actually drawing as sigma xx here, this sigma xx as well as this sigma xx, it is actually representing the state of stress at that point itself. So what we are actually meaning is that there is a plane like this, and this sigma xx is on this plane, and this sigma xx is on this plane looking at this side. Because it looks very cluttered if I draw it at the same place. That's why we draw this little element and draw all the stress components around it. Wait, however, if I actually take out a chunk of material, a block of material like this, then you please understand that over here and over here, it is not going to be the same stresses. Okay, if I actually take out a block of material and not consider a single point. Okay, so here it will be sigma xx, here it will be some increment over the sigma xx. Here it will be sigma yy, here it will be some increment over the sigma yy. Yes, your question.
So in that previous example, when you told that we are just taking for our
yes
of calculation,
yes,
so basically sigma xx, so both sides are on the same plane itself.
They are on the same plane, but with respect to different unit outward normals. One is along the positive x and one is along the negative x. That is the only difference. But now, if we consider the same kind of a square, but depicting it to be an actual chunk of material, then the situation is quite different. So this cuboid of material that I am drawing, it is in that sense. That sense means not in the point sense. It is actually a physical chunk of material that I have carved out of an actual body, which means that I have to be careful in writing about the stresses. Okay. So I have to actually incorporate the increments in the stresses. So first I will set up my coordinate system. My x is like this. This is my x. This is my y. This is my z. Origin is here. Okay. Now one by one I will draw the stress components. It is going to be an extremely cluttered drawing, but there is no way around it. This is sigma xx. First of all, what I will draw is all the stress components which are along the x direction. Okay, which are along the x direction. So there is a mistake here, but I have deliberately written it. Just bear with me for 1 second. Had this state of stress been referred to just a single point, then this would have been the correct picture. But this is not the correct picture now, because we have actually extracted this actual physical chunk of material. So on this plane you have sigma xx, but at an increment over this length, which is delta x. This length is delta x. You do not have the same sigma xx. What you have actually is an increment over sigma xx. Huh? Because there are variations in the stresses in the body.
But in the case where we put down this to 0 and
Which one 0?
E to 0, everything is like
Yeah, but you still have this divergence of sigma, right? This divergence includes all the derivatives with respect to the stress components. So I'm going towards that. So this sigma xx is at a certain point. This sigma xx is at a point which is at a distance delta x from this location. Okay, so what we'll do is we'll say that this sigma xx is actually, or this stress component is actually like this. What am I doing here? Okay, yeah, exactly, Taylor series. So if I come to this rough column, what I'm actually doing is writing something like this, that this was not supposed to happen at Nalanda. This was supposed to happen in another building in JCB lab complex. We got a notice for this. But my video is working, right? Okay. It will not probably pick up this thing properly. Charit, can you? Oh. So it is something like this: x plus delta x. In Mahabharata, Arjuna was found practicing his bow and arrow in the night. So we can do this. So sigma xx plus del sigma xx del x delta x. Okay, and then you will have the higher order terms which we are neglecting. Okay, so it is in this sense the Taylor series expansion. Now on these two planes we are going to have the components of stresses which are what? The tau yx. The tau yx is the component which is oriented along the x direction. There will be other components of stresses also. Here also you are going to have tau xy and tau xz, but it's going to be a cluttered mess, which is why I'm not drawing it. So on here you are going to get this thing, which is the tau. Very good, tau yx. And on top, this thing that I'm writing, this will be what? Tau yx plus del tau yx del what? Very good, del y. Because now what we are doing is we are looking at the increment of this tau yx as it varies over this length, which is delta y. I have not written it here, but it is what it is. Okay, this is delta y. Okay, and what should I write over here? This is into this del y or delta y. Similarly, for the other plane, this flat plane, I mean in the front and the back. So at the back we are going to have this thing. Okay, so you see already it's a horrible mess. So this is tau zx, very good, tau zx. And on this front face, so on this face, it is going to be, so that will be tau zx plus del tau zx del z into delta z. Very good. Okay, you understand that on each of these faces there will be two other components of stresses which I have deliberately not drawn. Okay, all right. Now we are going to write our favorite thing, which is the force balance. Okay, so So let's do that. We'll do the force balance in the x direction. By the way, I did not draw this. This length over here, this thing, this is our delta z. Okay. So force balance in the x direction, let's do this one by one. This thing, this component of stress, in order to make it a force, I have to multiply by a certain area. What area is that? Delta z, delta y. Okay, very good. So sigma xx plus del sigma xx del x delta x minus that thing, minus sigma xx, minus sigma xx. This entire thing should be multiplied with delta y delta z. Next, for this tau yx, okay, this tau yx. What is the corresponding area? Delta z, delta z, delta x. Very good. And finally, the same thing we are going to do for the the tau zx. This will be multiplied by which area? Delta x, delta y. This thing should be equal to 0. Okay. So if you simplify that, what will it look like? Del sigma xx, del x, delta y, delta z, plus del tau yx del y, delta y, delta z, delta x, plus del tau zx, del z, delta z, delta x, delta y, that is equal to 0. And lo and behold, the delta x, delta y, delta z are common, is common in all the terms. So ultimately what we have very beautifully is this. Please note that in this problem, had there been a body force, okay, had there been a body force which had a component in the x direction, you would have something like a rho bx, okay. So that also would have been multiplied not by the area but by the volume, and the volume of this chunk of material is nothing but delta x, delta y, delta z. That also would have gotten cancelled, and ultimately what you would have obtained is these three terms plus the rho bx, okay. So see, what we have obtained here via the force balance in the x direction is the first of this equation, which is referred to as a stress equilibrium equation, okay. So this is only the x component, so to speak, the x component of the stress equilibrium equations, which means that you should have the y and z components also. Now without doing the force balance, okay, because we appreciate symmetry, we will be able to write down the other two components of the equation, so to speak. Okay. So the first equation that we have just obtained, I'm going to rewrite it. This is just that same equation rewritten. Okay. Now next so this is for the x direction. For the y direction, if we do the force balance in the y direction, you tell me what I'm going to get. What will be the first term? Del tau xy del x plus del sigma yy del y plus del tau zy del z equal to 0. And finally, for the force balance in the z direction, what are we going to get? Tau del tau xz, very good. Del x plus del tau yz, very good, plus del sigma zz del z equal to 0. That's it. So these three equations together, they are referred to as the stress equilibrium equations. Okay, so around this in your copy, you put stars, balloons, very, very important, okay, ribbons and everything. Okay, after you go to your room, take a colored pen, put colored things around it, okay, and then you tear away that page and put it in front of you on the wall. Okay, like decoration. So these are the stress equilibrium equations, probably one of the most important things that you are going to learn in solid mechanics. Okay, not just solid mechanics confined to second year, forever and ever. Okay, so please, okay, give it the due respect it demands. Yes.
Sir, I had to doubt that we are since we are taking body force equal to 0.
Yes.
So what type of force will cause this type of stress distribution? Like,
Very good. Excellent question. I love this question. As if, so body force is not there, how will stresses develop?
sir, body force will be like
No. It's an absolutely valid question. I'm not mocking you. I'm saying this. This is actually a valid thing. I'm absolutely not mocking you. This is absolutely a problem. कि body force ही नहीं है, कहाँ से stress होगा? क्यों ही stress होगा? Okay, so we'll see. Okay, in the thick walled pressure vessel, how due to conditions at the boundary, things will develop. Okay, so you can think of it like this, that you have gone very, very far away from Earth and like deep into space, practically weightless. Okay, so practically zero body force, you're just floating. Now you have your companion astronaut. Okay, so he comes and he just pokes you. So does your skin not get stressed? It will get stressed. Of course it will get stressed. Okay, so that's how. So things may happen at the boundary of the body because of which the body can get stressed.
Because the force is external, so
But it is not a body force.
it is not a body.
It is a boundary force. Okay. What is a body force? So body force is something which is distributed on all the material points making up the body. Okay, but the boundary force, it will be confined either on all the points of the boundary or on a partial part of the boundary. Okay, both are external. Both are external. The question here is not about external or internal. Okay, the question here is on what part of the body it is acting. Gravity does not distinguish whether the points on which it is acting is on the surface of the body or inside the body. Your whole body is experiencing the gravity. Okay, but your friend poking you, that is just on your skin. Okay.
So,
Yes.
Hydrodynamics, this wasn't the case, right? Because let's say we have a cylindrical vessel of water and then we're just spinning it.
Yes.
We get that parabola shape.
Yes.
So for that, that B vector is just the, let's say, the centrifugal force that is. So there is no boundary or external issue there.
So let us assume that we are not going into the non-inertial frame kind of thing. Okay. You take the simpler case. Whatever you said, we take the simpler version of that. Suppose you have a parallel plate channel and you have the fluid which is static there. There is no pressure acting on the fluid. Now, if you slide the top wall, will the fluid not move? But there is no body force. Suppose you take this entire contraption, your entire device, this parallel plate channel, again into deep space. Okay, no body force, nothing. Okay, gravity is minuscule. So there also, if you slide the top wall, the fluid will start to move. How does it move?
So that is because of the viscosity internal.
That is because of what is actually technically referred to as the diffusion of momentum. So you have the top wall sliding, it drags the fluid which is just attached to its, to the adjacent layer. That layer in turn drags the next layer. So because of viscous forces, the momentum which is there in the sliding wall, that gets transfused to the entire fluid. But this is not a body force. Okay, so that exact problem can actually be started from this thing only. This this divergence of sigma is equal to 0. Okay, in fact, you can start with this stress equilibrium equations only. All that you have to do is substitute the appropriate stresses with the corresponding relations with the velocity terms. Okay. Okay. Now what are you going to do with it? So the second topic of the day is over. Okay, second topic of the day is over. It's a very, very major step. It doesn't look like much, but these are extremely important. Okay, as I said, put them on a piece of paper in front of you in your room. Now, what are you going to do with it? We are still, it seems we have not even started with thick walled pressure vessels, but the heart and soul of that we have already done. So see, in order to make our life easier, because we are so very familiar with the XYZ coordinate system, we dealt with the XYZ coordinate system. But whatever we have obtained, this entire thing, the stress equilibrium equations, this in a more compact form is nothing but divergence of sigma is equal to 0. So this itself, okay, the divergence of sigma equal to 0 in the Cartesian coordinate system, suppose you gave this to a mathematician who has never learned fluid mechanics or never learned solid mechanics, he or she will also write these equations only. Okay, so these are the stress equilibrium equations. Now the thing is that the stress equilibrium equations should be independent of the coordinate system that you have chosen. Coordinate system is just an engineer's choice or a mathematician's choice. We can choose to work with the XYZ system. Another engineer can choose to work with the R theta Z coordinate system. That should not change the fact that the stress equilibrium equations are actually working. It is only that in the R theta Z coordinate system, the stress equilibrium equations will look a little bit different. First of all, you are going to have different components of the stresses. Instead of sigma xx, you are going to have sigma rr. Instead of sigma yy, you are going to have sigma theta theta. And for the sigma zz, you will still have the zz, but you understand that is in the longitudinal direction. Instead of tau yx, you are going to have tau theta r. Instead of tau zx, you are going to have tau zr. So on and so forth. All right. Now, the peculiarity of maths and the idiosyncrasies of the non-Cartesian coordinate systems are such that when you deal with those, and you are probably familiar with it from your fluid mechanics, is that when we are working with the cylindrical coordinate system or the spherical coordinate system, the equations don't look so clean. Okay, they don't have this nice symmetry. Okay, some mischievous terms crop up. Okay, there is a 1 by r somewhere there is a 1 by r square. God knows, something like without even a derivative term also comes up. Okay, all sorts of weird things happen. Okay, so what we'll do for our purposes, Okay, so we'll take again a very utilitarian approach. We could, for the sheer intellectual pleasure of it, go on to a derivation of the r theta z coordinate system version of this stress equilibrium equations, but that would take probably another 2-3 hours, and doing it by hand also is not very fun. It is, however, very fun to do it in symbolic Python. Okay, but we'll not do any of that. Okay, this is not a maths class, so we just say that we have a certain form and we'll work with that form. The idea here is to understand the mechanics and physics of it. You have understood the physics of it, you have understood the mechanics of it, you have understood the geometry of it also. Now accept on good faith the equations that are there in the r theta z coordinate system. Okay, so I'll not even write the other so what we'll say here is that so along the r direction, what we are going to have is this. Yes, you want to ask something? Does anyone want to ask something? Okay. Sorry? Oh yeah, you. Doesn't make much difference, but let's be honest. Okay, so we have this thing. Okay, now this looks like a horrible equation. Okay, this is just the r version, and we are not even looking at the theta and the z. Now if some of you think that I have come to class after mugging up this equation so that I can impress you by writing this, okay, you are absolutely correct. Okay, I have literally mugged it up. Okay, there is no other secret. Okay, so actually the version that I know of, which I can say even in my sleep, is another version of it which we'll deal with, but this particular version I never remember, so I just mugged it up. Okay, the other two things I was too lazy to mug up. Okay, and we don't need it also, so that's why I did not do it. Now what we'll do is we'll immediately, as taking up our utilitarian approach, we'll try to go as fast as possible into the thick walled pressure vessel. Okay, what's the time now? Okay, so we'll go into the thick walled pressure vessel. Now thick walled pressure vessel gives us a very nice opportunity to simplify this equation. Okay, so this is what we are going to do. So from now on, we are going to discuss our thick walled pressure vessel. By the way, I think you have had a similar sort of discussion earlier in fluid mechanics. I want to just reiterate it for your edification and maybe a little bit of revision. So one small thing, allow me this indulgence to discuss that just before we go into the thick walled pressure vessel. This is for your general understanding of things. You see, there are three equations here. How many unknown components are there? So we will take it as given that tau yx is equal to tau xy, and all those things we will allow. That much we'll allow. So how many unknowns are there? 6. How many equations are there? Can you solve them? No matter how much mathematics you do, you will not be able to solve them. So in mathematical parlance, this is actually a system of equations which is not yet closed. Okay, so we have to close the system of equations. How can we do it? So you have had a similar sort of discussion in fluid mechanics. What are you going to do? Well, What is your problem? You don't have enough equations. Okay, now you cannot delete stresses. Okay, you cannot delete stresses. If you want to remove your problem, you have to bring in more equations. You're lacking equations, right? So all this while my philosophy was that if you have a problem in your life, remove your problem. But sometimes the problem is the lack of something. So if you have the lack of something, bring it. Okay, so we don't have enough equations, we'll bring in more equations. What more equations do you know? Not energy conservation. Energy conservation in last chapter, okay? And energy conservation is not sufficient actually. Um, so somebody said continuity equations. I just want to make it clear, you don't need any of these things for your mechanics of solid syllabus. Again, just for general knowledge. When we are writing these things, as we write this, you don't need to worry about mass conservation. But the earlier version that I wrote, that rho dv dt, that version, in order to arrive at that version, you have implicitly used the continuity equation. And please, for the love of God, do not ever think that the continuity equation applies only to fluid mechanics. It applies absolutely to solid mechanics also. Mass conservation is very much valid in solid mechanics also. Of course it is. I mean, chunks of material will not disappear out of into thin air. Okay, so mass conservation is absolutely valid. Okay, I am saying this on record. Okay, so continuity equation is absolutely valid in solid mechanics also. Okay, all right. So what other equation will bring? We will bring the stress strain relations. Okay, or the strain stress relations. The generalized Hooke's law. You know that is that you have been learning it since first year. So you have, the issue is that you are now stuck with 3 equations and 6 unknowns. What are the 6 unknowns? The 3 normal stresses and the 3 effective stress, this shear stresses. Now we are going to bring, so these are the stress equilibrium equations. Next we are going to bring in the 6 strain stress relations. Okay, the 6 strain stress relations. These are the equations. Okay, so these are the relations or equations. Cool. But what have you done? तो पैर पे कुल्हाड़े मार दिया. Huh? Okay, the 6 unknowns were the stresses. Okay, these were the stresses. And those 6 stresses appear here. Good. So far it was so good. But in the process of bringing these 6 strain relations, you have introduced 6 unknowns, these strains. Who will give you the knowledge of these 6 strains? No one. Okay, so what you have done now as a result of this is that you have done now this thing, 6 more unknowns. So let us do a balance sheet of this. Okay, balance sheet. So 9 equations. Okay, how many unknowns? 12 unknowns. It is like playing catch up. Okay, it is like playing catch up. So we are still lacking equations. Bring in more equations. Okay, bring in more equations. Throw everything that you have at it. What more do you have? Go to the strain chapter. What relations did you study there? First question of tutorial sheet and last question of tutorial sheet. Question number 1 and question number 14, I believe. What was it on? Yes. What was it? It was a strain displacement relations. The relations between the strains and the displacement. So epsilon xx is equal to del u del x, epsilon yy is equal to del v del y, all those things. Those are also equations. There's an equal to in between. Na? Okay. So what we'll say is that, and how many of them are there? There are 6. Okay. So 6 strain displacement relations. Okay, and now what have you done? So here you have 3 plus 6, 9, 9 plus 6, 15. But what have you done here? 6 plus 6, 12. Have you introduced anything here? the 3 unknown displacements. Okay, so plus 3 unknown displacements. So we have got back world peace. Okay, nothing to worry. 15 equations and 15 unknowns. Okay, okay. The mathematical problem is thankfully closed. All that you have to do to solve a situation is just solve these 15 equations.
I think it's all in the principal direction only.
Sorry,
The principal direction.
that doesn't help you.
So you would have what same access.
There is such a thing called conservation of difficulty. It is a law of nature. Okay, if you do higher studies, that is the fundamental law of nature. यहाँ पे cheating करोगे तो वहाँ पे काटेगा. ठीक है? All right. So we have 15 equations, 15 unknowns. We have to just solve this 15 equations. No problem. Okay, and this is what we do. Okay, of course, ultimately we don't deal with the 15 equations because we deal with specific problems. So when we deal with specific problems, ultimately it just boils down to solving one equation properly, which is what is going to happen in the case of this thick walled pressure vessel. Okay, so take a break of 5 minutes and then we'll continue with the thick walled pressure vessel.